Imagine a straight line from the origin of an xy axis system. Now imagine we rotate the line about the y-axis. We'll get a cone with its apex at the origin. The question is, what is the volume of the cone? So we've got a line from the origin with a gradient m, and then we're going to rotate that line around the y-axis to create a cone, and we want to find the volume of the cone. To find the volume of the cone, we're going to imagine an infinite number of infinitely thin disks that go from the origin, getting bigger as they go up the y-axis. So we're going to integrate the area of this disk from y is equal to 0 to y is equal to h, which is the height of the cone that we're interested in. The area of this disk is pi x squared, so we're going to integrate from y is equal to 0 to y is equal to h pi x squared dy. So our equation is the integral of pi x squared from y is equal to 0 up to y is equal to h. Now the problem is the equation is in terms of x and we're integrating with respect to y, so we need to find an equation that links x and y. By similar triangles you can see that r over h is equal to x over y, which means that x is equal to ry over h. R is a constant and h is a constant. So now we can substitute for x in this equation and we get that the volume is equal to the integral from 0 to h of pi r squared y squared over h squared dy. Pi, r and h are all constants, so we're just integrating y squared with respect to y. So the integral of y squared dy is y cubed over 3, and we can see that the volume is pi r squared y cubed over 3 h squared. So now what we're going to do is we're going to replace y with the upper limit. So y cubed becomes h cubed, and h cubed over h squared just leaves us with h. And then we're going to substitute the lower limit. So when we put 0 in place of y, the term becomes 0. So we can see that the volume of a cone is 1/3 pi r squared h. We can use a similar technique to find the volume of a sphere. As before, we'll look at the area of a disk parallel to the xz plane, and we'll integrate from y is equal to minus r to y is equal to plus r. The area of the disk is pi x squared, so as before we need to find an equation that links x and y. Well, we know that r squared is equal to x squared plus y squared, that's Pythagoras. So r squared is equal to x squared plus y squared, which means that we can write x squared is equal to r squared minus y squared. So if we substitute this for pi x squared, we're going to get the integral from minus r to plus r of pi r squared minus y squared dy. R is a constant, which means that the integral of the first term is going to be r squared y. Y squared obviously is a variable, so the integral of that is going to be y cubed over 3. So now we substitute the upper limit, so r squared y becomes r cubed, and y cubed over 3 becomes r cubed over 3. Then we subtract the value after we've substituted the lower limit. So r squared y becomes minus r cubed, and minus y cubed over 3 becomes plus r cubed over 3. So this bracket is equal to 2r cubed over 3, and this bracket is equal to minus 2r cubed over 3, but there's another minus here. So these two brackets add together to give us 4/3 pi r cubed, which we probably already knew, but now we've proved it from first principles. So we've now proved from first principles that the volume of a cone is 1/3 pi r squared h, and the volume of a sphere is 4/3 pi r cubed. So you should now be in a position to answer questions 19 and 20 of the questions on integration in the textbook.